Welcome everybody to another session from Nairo Research. I'm Srijit here, and in this session, I'm going to brief you about the applications of DFTB, so especially potential energy surface scan. So in AMS, as mentioned, it's a comprehensive software platform that allows to perform various atomistic simulations, including PES Scan or potential energy surface scan, using different computational engines. So one of the engines is the DFTB, which is density function type binding, which is a fast and approximate electronic structure method. So generally, how we can approach PES scan through or PES scan through DFTB in AMS. So let me brief you that how we can focus on DFTB in AMS. First about speed and accuracy. Obviously, DFTB is significantly faster than full DFT calculations, making it suitable for larger systems or for quickly pre-screening many systems. While it's an approximation, it can provide relatively accurate results for geometries, frequencies, and barrier heights, especially for systems with significant covalent character and minimal charge transfer. And then speaking about parameterization, DFT relies on pre-calculated parameters, for example, Hamiltonian and overlap matrices for atomic pairs, which contributes to its computational efficiency, and integration with the AMS driver. So the DFTB module or engine is fully integrated with the AMS driver, allowing it to be used for complex tasks like PES scans, molecular dynamics, Monte Carlo simulations, etc. Then it supports different orders of DFTB, including DFTB2, DFTB3, which accounts for charge transfer effect. DFTB3, of course, for instance, considers the variation of atomic chemical hardness with atomic charge. And what are the steps to perform this PES scan with the DFTB in AMS? So the thing is that I'm just showing you an overview that how we can perform the settings. So first of all, building up the system or import the molecular structure. So we can use the builder tool or the file menu for importing the structures. So I have already done one example by importing the coordinate file of a cyclohexene. Either can be XYZ or mol file. Ensure the atoms are correctly defined. So in this case, I have already defined which bonds to be selected. I have selected the C2 and C3. So it's a general overview that how we can do the calculations. I have already selected the engine from this main tab, so DFTB, and then after choosing it, I have run normal PES scan. So to show that how we can execute the calculations. So the main purpose is to understand that how this thing can be useful for understanding the starting value, the ending value, and also how to navigate the coordinates. So we can specify the degree of freedom that we want to scan, and also the distance between the atoms, the angle between the atoms, their dihedral angle or the torsion angle, the distance between specific atom pairs. So basically, this is the parameter that will help you to understand that what are the things that can be used to analyze between two atoms. So in this case, after running the calculation, I can show you that what could be the expected result. So this is actually the calculation result. You can see that at what point the bond got break and at what point the formation happened. So basically, it will help you to understand that how the starting geometry, for example, a good starting geometry is crucial for a successful PES scan, especially for locating the reaction pathways and also the coordinate choice. You can choose the scan coordinates wisely to ensure that how we can explore the relevant reaction pathway or conformation will change. And the number of points, the higher endpoints will give more detailed PES scan, but will be computationally more expensive for in the case of bigger systems. So then comes convergence issues as a part of this, it is constrained. Sometimes the constraint optimization at certain points on PES might fail to converge. So AMS has options like fill and converge gaps to help with this. And the most important thing is transition state search. So a PES can help us to find out an approximate transition state for more precise transition state geometries and frequencies. We can, use typically a follow-up method with a dedicated transition state search. For example, using the saddle search or transition state search task in AMS, often with more accurate DFT method. If the DFTB result is only a guess, then we can visualize the result. So right now I have shown you how to visualize the result using the AMS movie tool, which is an excellent, tool for visualizing the trajectory of scan and plotting the energy. So you can see the energy plot. So to sum up, all these steps and carefully considering the system of the desired scan, we can effectively use DFTB in AMS to explore potential energy surfaces. So to sum up, as an intro, these are the main points which I would like to convey. So let me stop here, and in the next video we will be focusing on how we can use this methodology in transition state search with another exam. Thank you, and for more information, I request you to kindly subscribe our channel as well as follow our LinkedIn page. Thank you.